Good afternoon. My name is Jean-Louis Briot. I'm a professor in the Zachary Department of Civil Engineering and holder of the Spencer J. Buchanan Chair at Texas A&M University. Welcome to the 18th Buchanan Lecture. After a few words of introduction, I was going to call on Professor John Niedzwiecki, head of our department, but John called me and told me that he's unable to come. I can at least give you some basic statistics on our department. 1,500 students, of which 400 are graduate students, 70 professors, largest civil engineering department in the country, top 10 ranking among public institutions, some $11 million of research volume. So that's some of the statistics on our department. After my introduction, I will invite Phil King to say a few words about the Geo Institute. After that, I'll have the pleasure of introducing Mr. Clyde Baker, who will deliver his 2009 Terzaghi lecture on uncertain geotechnical truth and cost-effective high-rise foundation design. Then I will have the pleasure of introducing Professor Kenji Ishihara, who will present the 18th Buchanan Lecture on forensic diagnosis for site-specific ground condition and deep excavation of subway constructions. After a discussion period, I'll ask Philip Buchanan to come and give the plaque to Professor Ishihara. The best way to find out about next year's Buchanan Lecture is to go to the Buchanan Lecture website around September of each year, and that website is on the cover of the booklet. I wanted to recognize a few people in the audience, people who have made the Buchanan Chair possible. And you know, thinking about the Buchanan Chair, this chair has allowed me to dream in my career and to be able to accomplish some of my geotechnical dreams. There's no doubt in my mind that without the Buchanan Chair, which generates about $80,000 per year, I would not have been able to achieve what I've achieved, including the presidency of ISMG. So I want to thank every one of you for your support of our program over the years. So, you know, a number of people, and it's always dangerous when you start acknowledging people by name because you're likely to miss a few names, and, but nevertheless, Dara Hooper, Doug Flatt, Bob Patton, Willie Bowman, Don Klinzing, Philip Buchanan, Harry Coyle, and many more. Actually, talking about Harry Coyle, I remember Harry coming to get me for the interview at the College Station Airport in March of 1978. The plane from Houston was a small puddle jumper, 7 seats, 1 pilot, Rio Airways. The terminal in College Station was an old hangar. Harry had an old pickup truck, and we drove to the CE department, and the geotech division was in the basement. The walls were green, the doors were pink, and there was no windows. So the beginning of the interview, I told myself, what kind of a place is this? But then I met the people. Chuck Sampson, Louis Thompson, Wayne Dunlap, Harry Coyle, the list goes on and on. I discovered a dedication to achievement, a contagious can-do attitude, and all this in a very friendly environment. By the end of the interview, the trend had been completely reversed, and I was sold. Well, enough of this before I get too mushy. Let's get back to the present. And I wanted to introduce to you our faculty. We have a number of them that were able to make it. Chloé Arson, Marcelo Sanchez, Zenon Medina, Giovanna Biscontin, Charles Albany, Jean-Louis Briot, and Bob Litton. So we're 7 strong. Again, this is a very strong, by the number of faculty at least, group in the country. Since I'm president of the International Society for Soil Mechanics and Geotechnical Engineering, I take unfair advantage of the situation to give you an update on our international society. So the website, you have it here, and you've seen that. Started in 1936. First conference, 20 countries, 200 delegates. Terzaghi was the first president. In 1957, ISMGE was more formally organized. And 2010, we have 86 countries that are members and nearly 19,000 individual members. And we're discussing the possibility of becoming the International Society for Geotechnical Engineering. Here are the past presidents. And you might notice right here, we have Professor Ishihara, who is going to be our Buchanan lecturer today, 1997 to 2001. So I'm number 15. This is the board. So of importance to you is the VP for North America, Professor Ovine in Mexico City. This is ISMGE today. The red zones are the member countries, so we have a few holes. There's about 200 countries in the world, and so we have 86 of them, and that's about, but you can see that we need to do more work in Africa, Central Asia, East Asia, and some of South America. Now, this is the way I've reorganized the society, created some new groups. We have a student and young members presidential group. These are 18 young people that meet with me about 4 times a year and have direct access to the president to tell me what they think should be done for the future of their society. A corporate associate presidential group, this is being developed. These are the 25 societies that are member of the International Society. Again, direct access to the president, because I would like to increase the participation of industry in a society that's dominated by professors. Technical oversight group, this is our quality control group. This is our customer service group. This is Susan Lacasse in Norway at NGI is leading this group. Harry Poulos in Australia is leading the membership group. I felt very fortunate that both Susan and Harry agreed to serve when I asked them. A young person here, Dimitris Zekos, assistant professor at the University of Michigan. We created an awards committee because we had very few awards in ISMGE. And I didn't think we could recognize all the people that do good work in the society. And then the ISMGE Foundation, which I started to help the poorer countries attend lectures like this or conferences, people that are not as lucky as you and I. We've been talking about regrouping the strength in the profession. Soil engineering, that's ISSMGE. Rock engineering, that's ISRM. IAEG, the engineering geology, and regrouping this into the International Society for Geotechnical Engineering. We tend to split things into little pieces and we lose strength. I think that if we can regroup these 3 entities, we will gain tremendous strength and help the visibility of our profession. I travel extensively, and I find myself in countries that are very rich. This is the tallest structures in the world. You will hear some of these structures from Clyde Baker a little bit later. He worked on this one, and he worked on this one. And this is the current highest structure in the United Arab Emirates in Dubai, 828 meters. And they're talking about building the first 1 kilometer high tower, the Nakhil Tower. And then I find myself next to those very wealthy countries in very poor countries. Going to Haiti, where the earthquake devastated the country, pancake buildings, very poor hygiene, 200,000 people died, 1 million people in tents, and really a lot of poverty. So I decided to create a foundation that raises money, and you can see the people here that have contributed at various levels to make it possible for the if you have a student, for example, from a relatively poor country, they can apply to the foundation to be able to get their paid trips and come to these things. We already have a number of corporate associates. We have 25 of them on this picture, and I want to acknowledge them, but that's not enough. The rock mechanics folks have 100. IGS, geosynthetics, have 130, and we're at 25. Somehow we need to really raise the number of corporate associates in our business. So if you have a company that has an interest in the international arena and you're not on these slides, I would like to talk to you. Why be a member of ICMGE? Well, it's pretty obvious. You want to help the profession at the international level. How to join? You can contact me, I guess. I'll give you more details. Toronto, October 2011, is the Pan American Conference. This is going to be a big one, and I would urge you to consider coming to this conference. And then the next international conference is in Paris in 2013, and that should be a lot of fun. So this is my family. This is my professional family, and I keep saying that helping ICMG is at the level of a family obligation. Copying the words of Kennedy, don't ask what ICMG can do for you, ask what you can do for ICMG. So I'm coming to the end of my introduction remarks. Now I'd like to invite Philip King to say a few words about the Geo Institute. Phil is the president of Synchropile, a company primarily dedicated to post-grouting of drilled shafts. He is next year's president of the Geo Institute, a definite friend of the academic group, a friend also of the practitioners, and a good friend of mine, Mr. Philip King.
Jean-Louis, 2 years ago, of course, was president of the Geo Institute, and that's where he brought up this professional family. And I think it's really very, very important that it is our professional family. You look at other noted societies across the country, the AMA Medical, and there's no doubt that that the technical spokesperson, the technical organization of the physicians is the American Medical Association, and that's who we are in the geotechnical world. And we, and I forget who said it, but some years ago, someone quoted the fact that, if a doctor has a mistake, usually one person dies. If an engineer has a mistake, multiple people die. But I don't know if we really deeply believe in that ourselves, and we should. We are a very important part of society. The Geo Institute, which, ASCE created the institutes a little over 20 years ago because they realized that ASCE was all civil engineers, but for the individual practitioners, they follow in these specialized groups. Of course, you have the Structural Institute, and then the Geo Institute. We are the geotechnical engineers. We are a part of ASCE, and I think for a long time, it just kind of went along, and fortunately, some years back, or a few years back, we realized that we really aren't going where we need to go with this. We are the professional family. So right now, one of the initiatives of the Geo Institute is to work in cooperation with other geo groups in the country, one of them being the ASFE. Another one is the ISSMG. Those are the first three groups of the coalition that others will join in. And the purpose of that coalition is to advance the practice of geotechnical engineering. Not to ourselves or to ourselves technically. We have the technical background, but it's our image to the general public. And this isn't just in the United States, but it's in the world. And us as geotechnical engineers, and then also as civil engineers. Part of this, if you listen to the news, you'll see these news announcements, the grade card for America that the ASCE has come out that shows that how we are very far, way behind, lacking in the investment in repair of infrastructures. You hear about the pipeline explosion in California, the large explosions a couple of years ago in New York City because of failing infrastructure. Our roadways. Joe Waxy and I were driving over this morning, and he was quoting, I think, $400 and something a year per person is what we need to expend into our the transportation systems here, and we're only about a third of that. I get that right?
$537 a year we waste sitting in traffic.
That we waste sitting in traffic. As you're waiting to go, it's $537, and we're only paying a small portion of that through our gas tax that we have now. We need to raise that gas tax to pay for infrastructure. But that's just a small burden of it. What it really is, the public perception that we are offering this very great service to the country, which we do. And you know, our whole purpose in education and practice and so forth is to better the environment, is to better the public, to better society. And that's part of we as Geo Institute are part of that. So we are moving forward with that. The one thing for the great many young students here, many students, you're very involved in ASCE in A&M or at Texas or at all universities, but you're going to drop out. The statistics is that many of you drop out, and some of you will come back in about 5 years from now, but a lot of you won't. And the idea is that ASCE and the Geo Institute has come up with programs to make it easier for you all to stay in the society, involved in the society from day one after you get out of school. So look into those programs. If you go work for a company, if you go work for a university, you have to stay involved in society. They are your professional society. And you all sitting out there are what's going to make the profession and the society better in the future. So please stay involved in society. There's another big program from ASCE and the Geo Institute, and it's called the AGP, the Academy of Geoprofessionals. And part of that is that you now, as a recognized expert in the field, in the geotechnical practice, you will be certified as a DGE, Diplomate of Geotechnical Engineering, which means that you have above the basic qualities of a geotechnical engineer, that you do have basically, you're not an expert because there's legal words with that, but you are recognized as a noted geotechnical engineer. This is not going to come to you as your students. It will not come to you for about 10 years. But in the practitioner world or in academia, this is something that you really should seek and be recognized and be not only put PE behind your name or PhD, but also put DGE behind your name on your signatures. And again, these are programs, the whole purpose of these programs is to elevate the bar, to raise the awareness internally to ourselves, but also the general public that we offer these services that are better to the society in general. So I was reading something the other day where the whole sole purpose of ASCE and the Geo Institute is to better society. We as engineers are out there to better society. And what helps us do that is by joining the society that we can put our efforts together by ourselves and in cooperation with the other groups to have the highest technical ability in the world and at the same time, hopefully, where the society will understand our benefit to them. And so that's the message that the GI is going to try to put out for the next few years as we go forward on that.
So now it's my pleasure to introduce Clyde Baker. But before I do so, I want to introduce his wife, Jeanette, who is here with us. Jeanette, can you raise your hand? We're glad to have you. And we appreciate all you've done to help Clyde and therefore our profession over the years. Thank you. Mr. Baker received his bachelor's degree and master's degree in civil engineering from the Massachusetts Institute of Technology and joined the staff of STS Consultants in the fall of 1954. He quickly rose to be chairman of the company, and he currently serves as senior principal engineer at AECOM, which I understand is the largest company in geotechnical services in the world. Over the past 50 years, he has served as geotechnical engineer for many high-rise built in Chicago. He has also served as geotechnical engineer and consultant on 7 of the 16 tallest buildings in the world, including the 3 tallest in Chicago and 2 of the highest buildings in the world, the Petronas Tower in Kuala Lumpur and the 101 Financial Center in Taiwan. As a result of his experience, Mr. Baker has developed an international reputation in the design and construction of deep foundation. He has been a leader in using in situ testing techniques correlated with past building performance to develop more efficient foundation design. Mr. Baker has shared his knowledge and experience with his peers through numerous conference and university lectures, technical articles, papers, and publication. He's the recipient of many awards, ASCE, Middlebrook, CAP, also the CAP Award. He's the author of the Drill Shaft Inspector's Manual, a very practical man. He was chair of the executive committee of the geotechnical division of ASCE. Now it's the Geo Institute. So he had my job, and he had the job that Phil is going to have next year. And he was also the editor of our journal. He's a member of the National Academy of Engineering and was the recipient of the Ralph Peck Award in 2000, the Terzaghi Lecture in 2009, you will hear it, and was selected in 2009 to one of the highest recognition our country has for a geotechnical engineer, and that is to be a hero of geotechnical engineering by the Geo Institute. The title of his 2009 Carl Terzaghi Lecture is Uncertain Geotechnical Truth and Cost-Effective High-Rise Foundation Design. Mr. Clyde Baker.
Thank you very much, Jean-Louis, for that introduction. Uncertain geotechnical truth and cost-effective high-rise foundation design. My talk is almost a summary of my professional experience. We geotech engineers understand that the ground varies and we're always faced with this problem. We don't really know the total truth. And over here, somebody's asking for us to come up with a really cost-effective foundation. Purpose of the talk, to share experiences gained over a 57-year career, which I guess now is 58 years. Developing cost-effective foundations for high-rise buildings. That's what my experience has been, having been in the Chicago area for so long. Including how judgment was used evaluating innovation, cost, and risk when geotechnical truth was uncertain, with the judgment based on experience and not necessarily rigorous statistical analysis. You will see that I'm more of a practical guy than theoretical. The major portion of my career has been spent in Chicago, which is very fortunate if you're interested in foundation design for high-rise buildings, because there's so many high-rise buildings in Chicago. One time I think we had 3 of the 4 tallest. I followed Ralph Peck in Chicago and gained from Peck's experience. You'll notice I'm wearing a bolo tie, and Peck often wore bolo ties. Chicago has been glaciated, and the glacial action has really controlled the Chicago foundation conditions. This is just a picture taken from one of Peck's bulletins showing the different glaciers that have come across Chicago, and you can see that Chicago is right in this area here. We have a sand layer on top of the varying till sheets. The softest till sheets are naturally near the surface, and they get denser as you go down. This is a picture showing the the Chicago profile and all the different foundation types that we use in Chicago. I think it's a great picture and it's a great profile because we can use all these different, and we do use all these different foundations, and we have problems. And the geology is such as we can explain the problems. In the old days, of course, they built footings and mats up on this stiff clay crust, and they didn't have soil mechanics in those days, so they kept building taller and taller until they settled too much. And then we developed caissons with the underreamed at different levels, depending on the loads. And at the different till sheets, we sometimes find water-bearing deposits which can blow in on us suddenly. And then we get down below the hardest hard pan, we have more water-bearing deposits, and then fissured rock, and then a good dolomite. Here's a picture showing some of the tall buildings that were built before soil mechanics, sitting on our crust. And how on earth you would build buildings that heavy sitting over soft clay? And the way you build it is it settles. And I think we've had as much as 18 inches of differential settlement on that auditorium building. Fortunately, because the clay takes time to consolidate, they were able to keep maintaining the building, repairing it, keeping it up so it looks pretty good. And today, you look at it, you don't know it's settled so much until you walk into it, and you step down to walk into it. And this is just a picture showing the typical caisson construction that was developed in Chicago. Timber lagging with steel compression rings to hold the lagging apart, keep the soft clay from squeezing in. So caissons were used mostly for heavy buildings starting shortly after the 19th century. Or is that the 20th century? Anyway, 1900. And then about 1919, there was a lot of concern with the bearing pressures that they were using. They were using like 12 KSF bearing pressure for the caissons. And so D'Esposito, the Northwestern Union Station, decided to run a load test. This is a major load test for that day. Again, this is still very early in soil mechanics, right? And you can see what was required to run a major load test. And in those days, it took a long time to run the load test. Today, we run them pretty quickly. Back then, it took a couple of months to run it, build up the load. And they got load up on the hard pan till about 65 tons per square foot. But they were pretty smart, even back then, and they said, well, how much of the load is carried in side friction? So then they dug a tunnel, a shaft along, down to the same level as the bottom of this test shaft, and they dug under it and created a cavern under it, and then reloaded it to see what load it could carry, and subtracted that load from the bearing, and still came up with some very high bearing pressures. And you would think, oh boy, now we can really up the bearing pressures on Chicago hard pan. Unfortunately, because now the 20s came along and they started building all of these 40-story structures in Chicago, and all of those 40-story structures could have been supported on the hard pan, except that when you get down above the rock and sometimes at the hard pan interfaces, you can have blow-ins of water washing in sand and silt. And the experience when that first happened, that you could see ground settling adjacent to these blow-ins. And then people started to realize, hey, if I might save a lot of money, but if I put my building on hard pan, and then somebody comes along next to me and goes down to rock, it could undermine me and cause me a lot of settlement. So in the 20s, when they built the big building boom in Chicago, all of those buildings ended up going to rock, and they didn't use that information that they determined from that high load test. So then what happened? Well, nothing was built during the Depression, right? Then post-World War II. what did we learn and how did we advance? Well, pre-1948, the allowable bearing and cohesive soil in our area was just determined by the unconfined compressive strength. And then with the Terzaghi-Peck book, 1948, the formulas shown there, the allowable bearing pressure in cohesive soil turns out to be about 1.3 times the unconfined compressive strength for individual shafts, bells. Then about 1955, Skempton came along and with his research and showing that for deeper shafts, you could go up to, it was 9C, 9 times cohesion for the bearing capacity. If you use a factor of safety of 3, you're down to you go 1.5 times the unconfined compressive strength. And if the soil has sufficient granular component to have an undrained friction angle, then maybe you can get higher using triaxial compression tests. And that's what we did on the 65-story residential tower. This was about the tallest residential building in the world when it was built in 1965. And with triaxial testing, we designed for bearing pressure of 30 KSF on the hard pan. However, that's time-consuming, takes a lot of time, is costly. Fortunately for Chicago and elsewhere perhaps, the pressure meter was developed by Louis Menard at the University of Illinois, and we started using it in the late 1960s. And the pressure meter, we've got Professor Briaud's book here on the pressure meter. So all of you probably know about the pressure meter, but it's a radially expandable probe that is lowered into a borehole at the test level and expanded radially, measuring the pressure and the deformation. And with this information, you can come up with design values for both bearing capacity and settlement. You get results that look like this. We always like to see an unload-reload, unload-reload cycle. When we do it, we go up to the creep pressure, which is when you start to get some additional deformation in the 30 to 60 second loading range, and this starts to curve up. That's defined as the creep pressure, and then we run an unload cycle and then a reload cycle, and you get basically two different modulus values. And in our geology, we've observed that alpha, the ratio of those modulus values, in our experience, is an empirical factor that you can use very effectively. Now, the rules with the pressure meter. These are the rules that we follow. We like to keep the dead load pressure plus any long-term real live load pressure, plus the effective overburden pressure to less than the creep pressure. Now, why do we want to do that? That's so we can predict the settlement reliability. We could perhaps go a little bit higher than that, but when the stress levels go above the creep pressure, you start to get plastic creep, more than just the elastic movement. So the formulas that have been developed on that, assuming that you're in the pseudoelastic range, then no longer apply. Settlement theories using the pressure meter data. Well, the two most common approaches are that used by Menard, and he developed his procedures based on a lot of load test data that he had, and then the other approach is just the elastic approach. You have to come up with an elastic modulus and just use elastic theory to predict the settlement. And the Menard's formula that he has developed, you can see the importance of the alpha factor. Because this section here is raised to the power level. And that's why it becomes pretty important when you're predicting settlement. And like I say, in our experience, we have found that be empirically related to the unload modulus divided by the initial modulus. Now, you can study these things, later, but it's not enough time to go into detail on this. But you can see the Menard divides his soil up into different layers, and his formula takes into account in a progressive way the deformation in those layers. And in the elastic theory approach, the settlement is just based on the geometry factors times the width times the pressure divided by the elastic modulus. And the geometry factors are determined by these charts, and I see I've got them called here Christian carrier charts. That's where I got them out of, but I think you can find them even earlier in other textbooks. Pressure for more cost-effective foundations. Okay, we've got this method now where we can test the ground in situ with the pressure meter, and there's a desire to maximize the cost of foundation elements below ground that can't be seen. People want to spend the money above ground where they can see it and not waste the money below ground where it can't be seen. That's very normal. And with the increasing role of the developer, this became even more significant. More pressure to increase the bearing pressures, reduce foundation costs. And that puts the pressure on the geotechnical engineer to push the edge on the state of practice, and that's where we are. Now, there's judgment required in evaluating geotechnical uncertainty and the risks involved with ideas for reducing foundation costs. We have to look at those ideas, but we have to weigh the risks, and then we've got to use our best judgment in coming up with this cost-effective foundation solutions. And in all cases, we need to know our local geology and building history. We can learn an awful lot by calibrating to past performance in other buildings. And then keep in mind, we may not know as much as we think we do, and I'll illustrate something of that in my own experience. Now, the different ways to reduce foundation costs: maximizing allowable bearing pressure, using a mixed foundation system, reusing existing foundations, using highly stressed piles as settlement reducers, and then finally having a remediation plan for construction surprises. These systems depend on being able to reliably predict your settlement. In my early days, structural engineers didn't want to mix foundation systems because they didn't have much confidence in our ability to predict the settlement. Now we're much better at it, and we mix foundation systems all the time. Now, here's examples of not knowing as much as we think, and I've been involved in both of these. Petronas Towers, major, it was the highest buildings in the world when they were constructed in Kuala Lumpur, and a very extensive testing program, a couple hundred pressure meter tests, two low case unload tests. And based on all this testing, a modulus was used for the ground, the Kenny Hill Formation, and it was close to the average unload-reload modulus, 250 MPa. And the calculations for settlement were based using this modulus, and the observed settlement was only a half predicted. In other words, what was actually observed, we did all this testing, and we predicted the settlement based on the testing, used the Menard pressure meter test, and the settlement was only a half predicted. Now, I will say that if we used the Menard formulas, or Menard procedures for predicting settlement, we actually came up quite a bit closer. But using the modulus as an elastic settlement, and the unload-reload modulus as the elastic modulus, we observed settlement was only half that predicted. And that was based on our Chicago experience. We had found that if we used the unload-reload modulus as the elastic modulus, we would be fairly close. Usually we still over-predicted, but fairly close. So that's why we used it. Moving on to Burj Dubai, we just had a consulting role. We were not the lead geotech. And we were smart enough in that role to listen to the local geotech and see how he came up with his procedures for settlement prediction. And he had some experience, and it was based on unconfined compression tests, basically, back correlated to experience. And he came up with an assumed modulus, which was used in the settlement prediction, that was equal to about 0.2 times the average reload modulus. And the observed settlement came out to be about 2/3 that predicted. Now, if we had used our procedure that we had found in Chicago to be successful, and the same procedure that we used in at the Petronas Towers, we would have been way off. We would have under-predicted the settlement because the ratio, the unload-reload ratio to the initial ratio at the Dubai was about 10 to 1 rather than about 2.5 to 1, 2.5 to 3 to 1 as it was at the Petronas Towers. Now, if we had just said, okay, we will use 3 times for our Young's modulus, we'll use 3 times that initial modulus, we would have been much closer on both cases. So, but our procedure was to use the unload-reload modulus, and you can see how we would have been way off if we had done it on Burj Dubai. So, here's a picture of the Petronas Towers, and I was asked what was the most challenging job that I ever worked on, and that's a tough one. And I thought, well, maybe I should say the Petronas Towers, because in the Petronas Towers, we're building the world's tallest buildings in a weathered residual soil over karstic limestone, major voids, major cavities in a canyon. Who would want to build the world's tallest building in that environment? But that was what the client wanted, and the assignment was that was what we had to do, and we had to keep the differential settlement across the mat from one side of the foundation to the other to less than half an inch, and we were able to do it by varying the pile lengths and so forth. If I have time, we'll go into a little bit more of it later. And this is the Burj Dubai, or now Burj Khalifa, I guess, which shows, I guess it's the current tallest building in the world. It shows the predicted settlement done with a nice computer model using the modulus values that the local geotech developed. And the predicted settlement was about 70 millimeters. I understand it's now settled in the range of 45 to 50 millimeters. Essential requirements. What are the requirements for for really balancing this uncertain geotechnical truth and cost-effective foundation design? The structural engineer and geotechnical engineer must serve as a team. They must have confidence in each other and communicate well with each other and with the architect and owner. There are some advices that go along with that. Know and understand your local geology. Compare and calibrate to known case histories in similar geology. Develop the geotechnical engineer and the structural engineer develop the exploration program together. Perform simple bearing capacity and settlement analyses before more sophisticated finite element programs, and then perform an instrumented load test program to failure when practical. You always want to load to failure ultimately, if you can, to really learn something. If you only go to the 2 times your design load, all you learn is that, yes, I'm safe going to 2 times the design load, but you haven't really learned a lot about the properties of the deposit. When operating at the limit of past experience, take small steps. If large step is necessary, be more conservative. Require a pre-construction contractor conference or consultation. Remember, design must be buildable. It's always important to get the contractor's input in that. And then go through the what-ifs and have a plan B ready if poor performance exceeds acceptable limits. If you've come up with an idea and you're pretty confident it's going to work, but there's a possibility that it won't work, you better have a plan B ready. Have adequate construction monitoring and quality control programs with required communication between field and design offices. And then assume but verify. It is always good to verify your assumptions. If it's not possible to verify, then you've got to be more conservative. Now, the selective case histories to illustrate these different points, cost-effective foundation solutions, there are 5 that I'm going to show. and they illustrate different things. AT&T building, which is the first one. This is a 65-story building, and it built where a former Bell caisson supported parking garage structure had existed. And in urban environments where you're putting up new tall buildings where old buildings were already there, you got a problem with the existing foundations. A couple of the cases that we're going to talk about, we reuse the existing foundations. Here, it wasn't possible to reuse the existing foundations, but they were in the way. And the bells, bells are down in this hardpan layer, and of course that's where you want to sit with your new bells for much taller structure. But you got your existing caissons in the way. So in some cases you can go under them and get them in the hardpan. In other cases you can't go under them and stay in the hardpan. You'd be down in this water-bearing, very dense silt sand and gravel. And so what do you do? Well, one possibility is, okay, we can't do this. We'll have to put it on piles or caissons to rock. Unfortunately, the budget for that was not, the developer didn't have the budget for that, so that wouldn't work. So he said, well, is there anything else we can do? Well, we said, well, if we can dewater that water-bearing silt, sand, and gravel, we can still put the bells there. So filtered dewatering wells were used to lower the waterhead in that deposit, and it was successfully completed. The settlement predictions were based on, the pressure meter test. We had good pressure meter data in the hard pan and also in this water-bearing dense silt, sand, and gravel. So using our procedures, how did we perform? The core predicted settlement based on the pressure meter testing was 0.95 inches. The perimeter predicted settlement was about 1 inch. Now the average measured settlements, and this was, it wasn't completed, it was only 70% completed when we were taking our settlement measurements. So it came out to be about 6/10 of an inch versus the 6 to 7/10 of an inch versus the 1 inch that was expected. So we were right on the money, let's say, maybe a little bit under. The actual observed settlements were a little bit less than we predicted, which is good. What were the risks in using this solution? Well, if the filter dewatering wells hadn't worked, we would have been in trouble. We would have had to use more wells to pull the waterhead down. But our judgment based on past experience was that 3 wells that we put in would be sufficient, and in actuality 1 well turned out to be sufficient, really sufficient. We put the wells in where in the borings we had lost all of our drilling water, so we knew it was very permeable, and that's what you need if you're going to try that. You need a permeable deposit, a permeable deposit that you can pull the water out that'll extend over the site. The next one. This is a very interesting one because it was a challenge. The developer wanted to build a new office building at the same site where an existing 11-story building had been supported on caissons, and he wanted to know how tall he could build on the same site. Well, one of the problems was the existing building, the caissons were so closely spaced that it almost took up the site. So you couldn't put in new caissons underneath old caissons and things like that, like we tried to do at AT&T. But there was a 3-level basement on this site. So the idea was, if we take advantage of that 3-level basement excavation, the amount of soil that had been removed, the amount of weight that had been removed by that 3-basement excavation, and then put a mat over all of the existing piles there, and then we could build on that combination mat on existing piles, taking advantage of all of that load that had been removed in the basement excavation. Now, how does this work? Well, the building load is distributed between the new mat and existing caissons based on the relative stiffness predicted by the pressure meter testing. And we did have pressure meter testing in all the layers. Here's the mat level. Here's the basement excavation. The existing caissons went down to this level here. We had good pressure meter data here, and we had good pressure meter data underneath the mat in this medium to stiff clay. Using the pressure meter data, calculate the maximum sustained load that can be carried by existing caissons without exceeding the creep pressure. Now, they were 100-year-old caissons. They were designed long before the pressure meter. And we thought, well, today using our pressure meter, we can probably load them higher than they were designed for before exceeding the creep pressure. And that's true, we could. So we determined that amount of settlement to be about 1 inch. And then calculate the amount of pressure that the mat can take for a comparable settlement, and then combine them. Combined loads at equal settlement represents the maximum sustained building load that can be applied. Using that approach, we went from the 11-story original building to a 38-story new building. And this is what it looks like with all those existing caissons. The structural engineer put in some stiffening walls where he felt he might need them. And it was a little bit more complicated than you first think about it because some of the existing caissons went down to rock, and the rest were up in the hard pan. There's going to be differential settlement between the rock caissons and the hard pan caissons, and how did it actually work out? Well, with the full structure dead load in place, but the live load not in yet, estimated at 70% of the total design load, the predicted settlement would be about 0.7 inches, right? It was all based on a 1 inch total settlement. And the range might be 5/8 to 3/4 of an inch. The measured settlement varied from 0 on this wall, the north wall that had rock caissons, to about 1/2 to 5/8 inch in the rest of the project. And then allowing for surveying accuracy, maybe the real settlement was between 1/8 inch on the rock caissons to 3/4 of an inch elsewhere. So the right ballpark for the most of the project. Now, what are the risks? So actually, I can tell you the project worked out very well. But what are the risks? The principal risk was under-predicting settlement. Existing caissons would be pushed into the ground with pressures exceeding the creep pressure, making them like settlement reducers. And with the corner of a building on rock caissons, excessive differential settlement could require mat supplemental micropiles and or stiffening walls to control differential settlement, perhaps even both. Judgment was the value saved by the combined foundation design was worth the risk. South Side office building. Well, you can see on this previous one, we're reusing existing foundation. Now, this is a South Side office building that's going to illustrate using settlement-reducing piles, and you'll see in an unusual way, and you'll see what I mean. On this project, it's only a 10 to 12. It was going to be 12 stories initially. I mean, ultimately, but initially only 10 stories, and it's built. There's a sand layer, and then the stiff clay crust, and then fairly extensive, very soft clay. And then normally where we would have hard pan, there wasn't any hard pan. There was a thin layer of stiff clay, and then very dense water-bearing sandy silt. So the desirable plan of putting in belled caissons here couldn't work because of the possibility of a blow-in from the water-bearing sand and silt below. And so the original geotech had concluded, and the original geotech had also looked at putting a mat up here, and it turned out the settlements would be up in the 8 to 10 inch range. And so the developer said, well, that's too much settlement. I can't afford to put this building on piles or caissons to rock. Is there any other solution? So we were called in as an additional consultant to look at it, and we came up with sort of a compromise solution, which involved using Strip footings up here, very wide strip footings supported over this sand layer so that it all acted like a mat. And then at the column location, so it's a good part of the load would be carried by that, of course. And then at the column locations, adding a straight shaft down to this very dense deposit, with the concept being that we could drill down straight shaft and put in concrete before we got excessive water inflow that would destroy everything, which would happen if we tried to put a bell on. So, but if we could go down with a straight shaft to this very dense deposit, we had run pressure meter tests down there, and with the concept of settlement reducing piles, you can allow that load down there to go up close to failure because you're not relying on the pile as a structural element. The idea of when you're using settlement reducing piles, you have to look at it. The purpose of the piles is to reduce the settlement, and not and it's the project would be safe without the settlement reducing piles. You're just using them to reduce the settlement. The reason why that's important in Chicago, and it's important anywhere, is if it's a structural element, it has to be load tested. And load tests, of course, had slowed down the project, had a lot of costs. If it's just a settlement reducing pile, you look at it as ground reinforcement, and it's not a foundation element that has to be looked at and tested in the same way. So you can allow the stress level to go up in that element, even up to failure in theory, as long as the failure is what I would call strain hardening failure and not a brittle failure. In other words, as long as it goes up like this and then like this, would be the dense frictional failure. This would be if it was a hard cohesive or brittle failure. You wouldn't want to use this kind of a settlement reducer if you had this kind of a phenomenon, because if you were wrong in picking this value, of course you want to stay up here, but let's say you were wrong and you actually went up over this point, instead of just settling a bit more, picking up enough load to balance things, you could actually have a failure. You'd drop back here. So you only want to use this concept of settlement reducing piles in a bearing situation like this, where you have this phenomenon and not this. Additional requirements for use of piles as settlement reducers without stress restrictions. Bearing capacity factor of safety of the footing or mat without pile settlement reducers is equal to or greater than 2, and the structural engineer must be able to design the footing or mat for the range of possible support conditions estimated by the geotechnical engineer based on the confidence level of the predicted stiffness values. Now, determining the appropriate modulus for settlement prediction, we had a lot of borings there with a lot of standard penetration tests. There was only one boring with pressure meter tests, unfortunately. And the pressure meter tests were at close to a boring, were at the boring where they had the highest, fairly high standard penetration test. So we thought we have to adjust these, the modulus down. So we adjusted the modulus down based on the average penetration data across the site. And we have found using the automatic hammer today that you get much more consistent energy, and the blow count is a much more consistent value than it used to be. So averaging the penetration data using the automatic hammer and then correlating that to our pressure meter data, and then reducing the pressure meter values proportionately seemed reasonable. And then we put an additional reduction in to the pressure meter value based on our judgment on the assumption that before we got the concrete in the shaft, there would be some loosening of the dense bearing silt from water seepage. Now, how did it work out? Well, it worked out very well. We instrumented two shafts. One of the shafts was at the edge of the footing, and another of the shaft was an interior shaft. And it's interesting to see that, normally you would think, well, the interior shaft would settle the most. In actuality, the edge shaft settled the most. And the reason the edge shaft settled the most, and when you think about it, you don't have that footing extending beyond the edge shaft carrying its share of the load. You only have the footing in the other direction carrying its share of the load. So you get the major settlement at the edge shaft and less settlement at the interior shaft where the footing is carrying more of the load. The actual bearing pressure turned out to be under the edge shaft, calculated out to be 76 KSF, and in the interior end shaft, a little under 50 KSF. Now, normally, if we were doing a design with the pressure meter and these elements were going to be designed as structural elements, we would have probably limited the bearing pressure to no more than 40 KSF. So here, by considering these elements as just settlement reducers, we were able to go to much higher stress levels. And the measured settlements worked out to be in that 0.9 to 1.25 inch range. This compares to 8 to 10 inches for a mat alone, and compares to our predicted settlement range on the order of 2 inch plus with these settlement reducers. So what it probably means is that we didn't have to reduce the modulus values for the possibility of loosening. If we hadn't done that additional reduction, we would have been much closer on settlement observation versus settlement prediction. But anyway, we wanted to be conservative, and it still worked. Risk versus cost analysis. Well, the primary risk of softer shaft bearing resulting in greater load carried by the strip footings and resulting in soft clay consolidation and settlement. Well, why didn't we core through a shaft and actually see what it was like below? And some thought was given to that, but we finally decided that we'd been conservative enough, and that that we could go forward without taking the time of doing that additional coring through a shaft and testing below the shaft. I suspect we were under a lot of pressure by the contractor and developer at that point too. 111 South Wacker Drive. Now this was another one of these projects where there was an existing building, and this happens to be a building, tells you what happens when you're in the business long enough. The building that they tore down, I was the original geotechnical engineer on. I was the guy that went down in the caissons to look at them to say that they were okay. In those days, the engineers went down in the caissons, didn't send a technician down. We went down and looked. And here they're taking my building down, right? Putting a new building up. And there was a 3-level basement, was saved, and it was used as a parking structure for a while. Then in 2004, the developer came along and wanted to build a new building there. He had a 51-story building that he wanted to build. Very nice looking building, as you can see. And this is what the foundation system looked like. All these gray shafts, of course, are the existing caissons that are already in there. And so we came up with a plan that involved putting a mat over those existing caissons and enough new caissons that would go down to the hard pan, that in combination with the existing caissons, they'd have to go below the existing caissons. And actually, by going below the existing caissons, they actually got into better hard pan. And the question was, do we have enough thickness above the water-bearing silt? And we did. And so we used a combination of the bells, new bells going down underneath the old caissons in combination with the mat. And then outside, these are all new caissons. And we did run into you got to remember Plan B, right? We did run into some problems. There was a building here that we had been involved in that went on rock caissons. The rock caissons were grouted. However, maybe the grout wasn't sufficient, and And when these caissons were built, they got too close to the water coming up the sides of the old rock caissons and blew in to the bells here and made it impossible to totally complete the bells. This bell was completed, but it was we were very concerned about the quality of it, and so we insisted on adding a micropile additional support here. And this one, the bell, it was so bad that it was totally wasted. We had to put in a new rock caisson all the way down to rock, and ignoring the bell totally. This is what the profile looked like. We did a lot of pressure meter testing. You can't probably see it here. You can look in the paper to see what it's like, but there are different design levels. The old bearing pressure level on the hard silty clay, this is where the existing caissons were. The new bearing level down on the somewhat better hard pan is down here. And then deeper, we've got the very dense silt, sand, and gravel water bearing that we want to stay above. And so this is the design envelope that was used for predicting bearing pressure and settlement. Problems and remedial action. Well, I mentioned the unanticipated water problems encountered at 2 caissons and how we resolved it. Now, the interesting thing is the 14 rock-socketed micropiles in Chicago, if you use piles, you have to load test them. So we didn't load test them because we convinced the city that they were just supplementary, and that we were in a way using them as settlement reducers, because we calculated the elastic compression in the steel of these micropiles, and it was sufficient that amount of settlement would, at a reasonable bearing, at a reasonable stress level, would be sufficient in balance with the as-built caisson, so that it would work. And we convinced them in a way that we didn't have to do the load testing of the micropiles. On the rock caisson case, we don't have to load test rock caissons. You do got to case them, permanently case them down into the dolomite, and test the dolomite, and that was done on the rock caisson one. How did it all work out? Well, it worked out very well. The settlement predictions were typically 1 inch or less, and the observed settlements were typically less than 1 inch. And it was interesting, where would you guess the maximum settlement was that was measured? It was on the caisson that went to rock. Now, how can that be? How can the caisson going to rock have the maximum settlement? Well, it's always possible in our dolomite to have seams and fissures that are missed, and you can get a little settlement in closing up the fissures. When I say a little bit of settlement, that maximum settlement for that caisson, the total settlement was only 0.88 inches, so it wasn't a lot of settlement, and it compared with the other rest of the project where the measured settlement was in the 0.5 to 0.8 inch range. So everything fell into the same general ballpark. What were the risk versus cost evaluation here? The risk versus cost of reusing existing caissons were considered negligible, as complete as-built records were available. The risk of new caissons getting too close to underlying water-bearing silt and blow-in occurs. We didn't think that would happen, but if it did happen, we would have to use filtered dewatering wells to lower, like we did on the AT&T building. But we didn't think it was necessary here, and it turned out it wasn't necessary. The internal lateral blow-in that did occur, it wasn't anticipated, but you got to have a backup plan, and we had a good backup plan for both of those caissons where the lateral blow-in did occur. Petronas Towers revisited. Take a little more time on Petronas Towers, because in the end I come up with an idea I want to throw out, and why I don't think it would have worked. In the Petronas Towers, we did a settlement analysis, a preliminary settlement analysis, what I call approximate analysis using approximate methods, and we came up with predicted settlement. 60, you can see here, we're using the pressure meter data. We come up with a settlement calculation using the elastic theory of almost 60 inches. Millimeters. And then you got to add the elastic compression in the shaft down to the equivalent footing level. And it's adds another 14 millimeters. And the total predicted settlement using elastic theory then is up around 73 millimeters. However, using the Menard method and his empirical method, the total settlement came up to about 41 millimeters. The actual settlement now, what was the actual settlement? Well, here's this, the computer-generated settlements are also up around 70 millimeters, but in the computer-generated settlement, this is what we had to do. You couldn't do this by approximate means because of the sloping rock and everything. The predicted settlement with the sloping rock, the variable length piles, trying to keep the settlement to less than half an inch across the mat, and the computer-generated settlement, you can see, is just a little bit less than half an inch. In other words, we just barely made the criteria. I see from one side to the other, we're going 54 to 65, and the other direction, 57 to 60. We're just barely making it on the half inch being, what, 12 millimeters. So we're just basically making it. Now, how did it turn out? Well, this is the plot of the actual settlement. Maximum settlement is like 35 millimeters. So the actual settlement was way under what was predicted using either the Menard procedures or elastic theory. Well, how could we be that far off? Well, we thought about it as a couple of reasons we could be that far off. One is, you notice how this slope here, and then like this, we did not include any pre-stressing effect for the piles. Actually, the piles were actually barrettes, but in principle, it's the same thing. They were installed before excavation. So and then you're doing a 20-meter excavation after your piles are already in the ground. And those piles then serve to kind of like pre-stress the ground. So now when you take that load out and the ground is kind of pre-stressed, now you build your building. And for the part of it anyway, until you get that load back on, you have a flatter slope. Then, okay, now we're getting a real good slope here. And then, just gradual, maybe a little continuing slope as we're loading, live loading the building. Another possible explanation, in addition to what I just said about the barrettes, was maybe a stress spreading faster than assumed with elastic theory. Then the other was that the proper soil model is not being used. Well, this is true. We knew that in advance, of course. The proper soil model is likely nonlinear with increased stiffness at smaller strains. And, this is what it is. At the smaller strains, the ground does behave stiffer. Hindsight evaluation of cost-saving foundation idea. Why not consider piles as settlement reducers and allow much higher concrete stress levels and only slight increases in predicted settlement with reduced concrete cross-section? We got very dense residual soils. Our mat is sitting on very dense residual soils. We don't even need piles except for settlement. In other words, there's an adequate bearing capacity so that sort of a perfect case for using settlement-reducing piles. The factor of safety is adequate. I'm sure it would be more than 2 for a mat only. The problem is that using it as designed, using those piles as designed, following code allowables and everything, and the stress levels in those piles, we still just barely made it settlement-wise. We just barely made it the half inch across the mat. If we had increased the stress levels in those elements, and let's say we could double the stress level in those elements. If we're now looking at those elements as settlement reducers or ground reinforcers, not necessary for the structure, but just to reduce settlement. So we could double the stresses in those piles, make them half as big. Well, of course, if you do that, the elastic compression in those piles have to be added to your to your settlement. And they're variable length piles. There would have been, we would not have stayed within our half-inch maximum criteria across the site. So, well, I think it was a good idea in hindsight. I don't think it would have worked. However, if I did another job there, I would consider using piles just as settlement reducers. Use a mat and just use the piles as settlement reducers because the ground is that dense. The average blow count in that residual soil is at 100. You know, that's very dense soil. Conclusions. Innovative, cost-effective solutions to foundation design problems are often possible using combinations or mixtures of foundation elements, provided that ground deformation in response to structural loading can be reasonably predicted within allowable tolerances. Even though geotechnical truth is uncertain and the design ideas are at the limits of foundation practice, the key requirements are geotechnical engineer and structural engineer teamwork, knowledge of and experience with local geology and past building foundation performance history, or being more conservative where such information is not available. Having experience with use and interpretation of in-situ pressure meter testing, or whatever method is used for predicting ground deformation under load in a particular geology, and having a plan for addressing geotechnical surprises. And then finally, being more conservative when assumptions can't be verified. The end.
Do you have any questions? Yes, sir, Joe.
With pressure meter testing, and you have the creep limit, that's lateral, radial lateral.
Yeah.
The Poisson's ratio, would you expect the vertical to be greater than lateral?
You know, I said I wasn't theoretical. I'm using an empirical method that works in a particular geology. So we have professors here that could answer the theory, but I really can't. I understand the theoretical limitations that way. It is a lateral test, not a vertical test. But in soils with isometric properties, at least, it's certainly been very, very useful. And so we're using it all the time. Do you want to comment?
I can give it a shot. Actually, what's surprising, you know, that this is a common problem that people mention. Pressure meter pushes horizontally, but I'm pushing vertically, so one is not directly related to the first one. But when you put a foundation on the ground, the load that you can put vertically consists of the resistance in the vertical direction and the resistance in the lateral direction. If you had no lateral supports, your foundation would only have 1/3 of its capacity. At least in clay, you know, 2 SUs, we can show it. So when the pressure meter pushes horizontally, there's a lot of the contribution to the resistance that comes from the vertical. So yes, we're pushing horizontally in one case and vertically in the other, but it's just not one completely different from the other. The mix of vertical and horizontal resistance to wherever you push, this way or that way, includes both.
That's a great explanation, thank you.
Thank you.
Any other questions?
Are you using pressure meter also for estimating the lateral capacities?
In what situation? Like for pile loading? For PY curves and stuff like that in pile loading? Yeah, sure, yeah. And we do use it that way.
In fact, in my opinion, that is the best use of a pressure meter. Because in this case, you don't even have the problem of pushing this way when you're trying to predict this way. You're pushing this way and you're pushing that way. So the analogy is much closer.
Yeah. That's
Any more? Bob?
On your projects, who is measuring, how are they measuring the cell?
Oh, these are just optical survey measurements, and they're only accurate to whatever you would say. You know that. Now, on some, some of these projects, though, are they're strain measurements too, strain gauge measurements in the shafts, but that's good for shaft deflection. But as far as the ground settlement, building settlement, we're stuck with sort of optical, or at least we have been stuck with sort of optical measurements.
I guess you need a deep benchmark when you have a hammer like a petromass tower. I mean, that make sure you.
Well, if you were going to do it right, but you're just measuring it to other local benchmarks.
Basic question.
Yes, please.
When you refer to sediment, what kind of sediment? Sediment after the completion of the building or during construction?
Both. Up to the point where when we're predicting settlement, we're predicting settlement. We have to include both, of course. And in our glaciated deposits, we are assuming that it's in the pseudoelastic range, and there isn't much settlement after construction. So basically, we're predicting the total settlement of when you put the load of the building on. And then we're measuring that total settlement because by the completion of the building, they're taking their settlement readings. Now, do they go back and see what the settlement is 5 years later? No. No, we don't know. Well, in one case we did. Yeah, that south side office building, the settlements were taken about over a period of years, and 5 years later, what we're showing there. So occasionally, we do have the opportunity. If we're doing it ourselves, we can go back. But oftentimes, we're not doing it ourselves. Somebody else is doing it, and we're just stuck with what they give us.
Over a certain period of time after completion of it.
Yes. No, not for a certain period of time after completion of the building. I would say the people doing the surveying are through at the completion of the building. They do not continue settlements. They now occasionally, like I said on our one project, we did it. We did it ourselves, and we did come back after 5 years. But normally, no, the settlement stops unless you're building on a deposit where you expect settlement to continue, and then you have to take continuing settlements. But if your design is based on not exceeding the creep pressure, remember, not exceeding the creep pressure, we're staying in that pseudoelastic range. We're really not expecting long-term settlement. So we can't convince somebody to pay us to go out there and to measure it. Yes?
How can you dewater that silt layer and not cause increase in hydrostatic pressure and settlement of the adjacent max supported foundation?
You're talking about that AT&T project? Well, you probably have, you know the hard clay acts as an aquiclude. So there's no connection over a short period of time, of months. Maybe 50 years there's a connection, but not over short periods of time.
To thank Clyde Baker for delivering the 2009 Tuzagi Lecture at the occasion of the 18th Buchanan Lecture, Texas A&M University, and it's signed by John Niswicki, department head, and Jean-Louis Briot. I don't know who that is.
Thank you very much.
Thank you. Now it is my pleasure to introduce Professor Kenji Ishihara, who graduated from the University of Tokyo in 1957. After a period of research at the University of Illinois under the advice of Professor Peck, he returned to the post of associate professor at the University of Tokyo. In 1957, he became a full professor of civil engineering and remained at the University of Tokyo for 40 years. During this time, he was active in the International Society of Soil Mechanics and Foundation Engineering. At the time, it was Foundation Engineering. Mid-90s, it became Soil Mechanics and Geotechnical Engineering. He was particularly effective in advancing the work of Technical Committee TC4, Earthquake Geotechnical Engineering, and in establishing the new discipline of earthquake geotechnology. His work with ISM-FE culminated in his appointment as president of the International Society for the term 1997-2001. Now, I have to tell you that during that period of time, I became very interested in work related to soil erosion and scour of bridge foundation, and I proposed a new international committee to Professor Ishihara, and he was kind enough to select me as chair of that committee, so I appreciate the chance that he gave me to have an impact at the international level. On his retirement from the University of Tokyo in 1995, he took up the post of Professor of Geotechnical Engineering at the Tokyo University of Science, and then at Chuo University since 2001. Professor Ishihara was the 1993 ranking lecturer in the UK, delivering the lecture on liquefaction of flow failures during earthquake, and the Terzaghi orator at the time of the 14th International Conference on Soil Mechanics and Geotechnical Engineering in Hamburg in 1997. In the United States, we have the Terzaghi lecture. We just heard Clyde Baker. And then in the international conference, there is the Terzaghi oration. So we have these two lectures. So we're obviously in a very good company. He was the recipient of the Seed Medal in 1998 from ASCE and several other major awards. He received the Japan Academy Prize in 2000, was elected in 2010 as a Foreign Associate of the United States Academy of Engineering. In 1996, he published his book, Soil Behavior in Earthquake Geotechniques, which summarizes his life's work. This book was actually translated in Russian in 2006. Professor Ishihara is the 18th Buchanan lecturer. The title of his lecture is Forensic Diagnosis for Site-Specific Ground Conditions in Deep Excavations of Subway Construction. Professor Ishihara.
Good afternoon, ladies and gentlemen. Thank you very much, Professor Burio, for your kind introduction. As a matter of fact, I'm very pleased to have him elected with the overwhelming majority to the president of the International Society, because he was the second president after Ralph Peck elected from the United States. And also he worked very hard for the well-being of the International Society, as he mentioned. And when I was the president, he made a proposal, and he was so enthusiastic and so outstanding. Actually, I have had no choice but to accept it. Today's talk is entitled Forensic Diagnosis for Site-Specific Ground Conditions in the subway construction. As a matter of fact, in 2005, December 4th, there was a big accident in Taipei in the subway construction. At that time, Dr. Wei Li was a Secretary General investigating the cause of the damage, and he asked me to join the panel for experts in Taiwan. Then I accepted it, and I learned a lot from the accident. And then in 2008, April, there was a conference, in situ conference in Taipei. At that time, everybody in Taiwan, geotechnical engineers, wanted to have this accident presented at the time of the conference. And however, because I was a very considered neutral man, they asked me to pray to make a presentation. So then I did some studies. So this is the basis of my of the current today's presentation. In addition to that, I got a lot of information from Japanese engineers and from Professor David Haidt on the collapse of subway in Singapore. So these are the two big ones. The third one is the another biggest one in Shanghai. So there have been three biggest accidents in the Asian region, or as well as, or I must say, in the world in the 21st century, related with the subway construction. So today's title is the introduction of this aspect. First of all, I'd like to tell you about the interesting picture which was taken at the time of a first international conference on soil mechanics and foundation engineering, which was held in Harvard University with Dr. Terzaji and Casagrande as acting secretary. This is a picture taken at that time. If you enlarge this portion on the right hand, there is a Professor Buchanan. I think this is a man, very similar to this diagram, as you can notice. And in this picture, Terzaji is here, and Casagrande is here, 76. So please look at this, his pictures very carefully. The other section of these pictures around here, there are quite a few very important persons. For example, you can see Donald D. Taylor, who is here, and Navarro Carrillo from Mexico, this man, and Burmester, I think this man, and Jerry Osterberg here, and Proctor's and Chebotaryov is this man. So these are very memorial pictures. So later on, all of these people became very famous and contributed greatly for the advancement of the geotechnical society, geotechnical engineering. A collapse of braced system in Singapore took place on April 20, 2004. The location of the Singapore, as you might know, here at the tip of the Malaysian peninsula, and the Singapore is, this is the Singapore area. There is a river, which is called the Singapore River. The accident have taken place in this section in the new subway line under construction. This is an enlarged map. This is the Kardong Basin Inlet to the south. This is the new line under construction. And the construction was under progress in this section, which is called Nicole Highway. The collapse have taken place at this location. At the time of the collapse, there was a people living in the apartment house, and one or two of them took a series of pictures. This is just before the collapse of the subway. You can see the service shaft, vertical shaft, transporting the material to the construction of the subway. This is a braced cut. Actually, the collapse have taken place, first of all, for the collapse of the braced excavation at this portion, followed by accompanied by the soil movement this way, and also the soil movement took place in this way. This is a pictures taken immediately after the accident, which took place on April 20th, 33 minutes past 3 o'clock. Fortunately, there was not many traffic in this Nicole Highway, so nobody was dead in this accident. However, in this portion, the workers were still struggling for recovering this accident, so they were involved in the collapse, and four persons died. This picture shows the detailed of the collapse. This is a vertical shaft, 70 meters in radius. You can see this black spot is a diaphragm panel on the northern side and the southern side, which was found after the collapse. So you can see the soil movement this way, and there was a borings made before the accident, For example, ABH 83 and so on. I will show you this soil profile later on. A more detailed map of the braced excavation is shown. There is an open shaft. So these brown dot indicate the board pile which had been installed before, as shown here. This is the side view of the excavation. Before the excavation, they installed the board pile from this depth to this depth to provide the basis for the subway, which was going on, which was planned later on. If you look at this location, which is the point of initiation of the accident, there was no board piles because of the 66 kilovolt electrical cable crossing this location, but it was at the shallow depth, say 5 meters from the ground surface. It appears that practically there was no influence of this cable. However, one of the board pile was missing. So please remember the name of the strut 335, 334, and so on. At the time of the accident, the excavation was going on here. First of all, engineers installed a diaphragm wall as well as the board piles, and also there are two jet grouted strut. And this the upper one was to taken away because the excavation was supposed to go down to a depth of this location. You can see two measures of the height. This indicates the depth counted from the ground surface. And in many of the countries, the elevation was taken at 100 meters below the average sea level, and count the elevation starting from the 100 meters deep. So there is a 6.9 meters, 4.2 meters, and so on. This is the elevation counted from 100 meters. And this jet grout is called sacrificial grouting. That means that it is a temporary support, but after installing the steel bracing, it was going to be taken out by excavation. At the time of accident, 3:34 p.m., the scenery of the accident looks like this. As you can see, there is a huge amount of soil slid down into the space, excavated space. 3:41 p.m., that is 7 minutes after the accident, everything looks like this. So partly the Nickel Highway was involved in this accident. This is the pictures showing the spreading of the different construction materials. There is an apartment house just behind. This picture show the installation of the jet grouting from the ground surface prior to excavation. So jet grouting has been used quite frequently, but its quality is very important, and its quality depends upon the skill of the contractors. At the time of the design and feasibility studies, several boring was performed to investigate the soil condition. For example, ABH 31, 84, and also 30 and 32 there. And the contour line was drawn based on the soil boring, which was performed about 20 meters or 30 meters interval of distance, which is considered as normal. If you look at the boring data on 30s, that is located here, it looks like this, indicating the fill materials near the surface underlain by the silty organic clay and further underlain by a very thick stratum of marine clay, which is designated by M. And then silty sand and silty clay, silty layer exists below this. So, and then over OA layer, which is called OA layer, exists below this soft marine clay deposit. And this was considered as a basis for diaphragm installation. The another boring data, that is ABH31, that is just here, indicates similar ground condition, except that there is a stiff materials in between, but overall, this layer is considered the Kowloon marine deposit. The other boring data, ABH32, where you can see a similar stiff materials in between, underlaid by the gradually increasing alternative layer of sandy silt and silty sand, which is called OA as a whole. This is ABH84, closest to the position of the failure. Particularly notice is the fact that the depth of this bearing layer is deeper than the other portions. So it is suspected that the diaphragm wall tool did not reach the stiff layers, OA layers. According to the design, the diaphragm wall should penetrate 3 meters deep from the top of the OA layer. After the failure, a lot of investigation was conducted, as shown here, which consists of the 2-meter intervals borings in the northern side, and also in the southern alignment, there was a borehole where they encountered a lot of obstacles because of the existence of the machines, buried machines, and so on. After the accident, everywhere was buried, and the new line was planned in the southern side. So there was no exactly verified data regarding what kind of bracings and diaphragm is existing. But this is just based on the surface observation of the diaphragm panel. These two were buried. If we look at the cross-section A66-, it looks like this, where you can see there was a sinking of the material on the order of 5 to 10 meters because of the involvement of this area into the general slide into the open space, and also the sliding plane was here. So of particular notice is the sinking of this F2 layer, intermediate layers on the order of 5 meters and so on. And OA, over-consolidated stiff layer, is located somewhere around here. There's another pictures that is a cross-section. Similar behavior can be observed, as shown here regarding the soil stratification and its deformation. Now, after the accident, based on the lot of additional borings, contour lines was drawn again. If you compare the contour lines in the previous diagram with this one, it is apparent that there is a very steep slope in the buried OA layers along this way, and which extend towards the north. But this buried valley was missed at the time of the design and feasibility study. That was the major reason why this kind of big accident must have taken place. Well, after the collapse, there was several borings was made, and this is one of the after the event soil profile indicating a very stiff material, which might be the hard cement, grout, or metals, and so on. This is a similar soil profile data after the accident. This also shows the same diagram. So the toe-in, the length of the diaphragm wall penetrating into the stiff layer was suspected to be the cause of the damage. So by taking the top of the OA layer at 0 point, the SPT N values was picked up and plotted in horizontal direction versus depth, coming up with a diagram as shown here, where pre-collapse boring data is shown by blue colors, whereas post-collapse boring data are indicated by red colors. As you can see, according to the design, the diaphragm wall 2 should be embedded into this level. However, you can see the SPT N values is not strong enough on the order of 10, 20, 30, and 40. Even below this, it is not stiff enough. Summarizing all the data, soil profile data was arranged in alignment on the southern side, taking this is the east and this is the west side. The areas indicated by M3 is the area of collapse. Superimposed in this diagram is the top of the OA layer at the design stage, as you can see here. This is the bottom of the recorded diaphragm wall. So you can see diaphragm wall penetrate pretty deep below the top of the OB layer. But if you look at the critical areas, somewhere around here, it is there is a estuarine deposit designated by E here and here, and also this is the OA layer, but the strength was not good enough. So because of the lack of the penetration of the tool of the diaphragm wall into the competent material, the movement of the tool must have taken place inward towards the excavation. The April 20th to 20th in 2004, excavation was going on from this area to here. So at the time of just accident, the excavation was advancing westward at this location. And in the morning, on the same day, there was the sound of metallic collision, which was heard somewhere around here and here. But at the time of 2 o'clock in the afternoon, the metallic collisions noise becomes more frequent. So workers within these strutted areas started to feel the concrete on this joint and so on, but it was too late, and also the countermeasure was not helpful. There was a observation of the inclination at this location, at the time of the before the accident, and I will show you the records of 104, which looks like this. So on 17th of March, displacement of the strut started to increase reaching the level of about 43.5 centimeters at this location at April 20th, 1 o'clock in the afternoon. However, accident have actually took place at 3:31. So there was a time lag between this measured time and the accident that was 140 minutes. However, we should be careful in looking at this data. Normally, this is established based on the inclinometer data. The inclinometer data gives the angle of inclination. And based on these data, this curve was established. But assuming that this is a 0 point. So this is a very tricky distribution. So engineers at site show that this point must have moved further towards the excavation, bringing the two of the diaphragm wall towards the excavation. And this must have been a genetic cause of the damage. There are two things to be considered very carefully. As we excavate downwards, the weight of the diaphragm is pretty heavy, so there is a reduction in the friction in the inside of the wall. So the diaphragm wall must have sunk down to some extent. And at the same time, because of the movement of the two of the diaphragm wall, the materials underneath must have lifted to some extent, raising the king post upwards. So there must have been a gap, as shown here, between the between wheels and the strut. So this kind of offset was apparently observed. At the time of the accident, the offset was almost 20 centimeters. So this was the generic cause of the accident. According to the report of the Committee of Investigation, which was publicized 1 year afterwards, the cause of the failure was attributed mainly to the overestimation of the soil strength around here, and also the poor design of the sheet piles and strut and welding and so on, and also the calculation was not so good. But later on, in situ engineers felt great doubt about this. Then he invested a lot of money to investigate a further site condition by making boring. This is a brace system before the accident. So one of the lessons we should take seriously is the connection between the strut and king post. And normally, strut and king post is rigidly connected here. So if king post goes up, the strut should go up also. And also, if a diaphragm wall sink, the strut was bent, and there are some breakage at the connection. This is one of the bad experience we should keep in our mind. So this indicate just the configuration at the strut. In order to reinforce this connection, they put additional plate stiffness in this fashion, and also channel stiffness in this way, but it was not useful. One of the scenario of failure is as illustrated here. Because of the inward movement of the diaphragm wall, soil moved upwards inside, bringing the king post upward together, and then there was a disconnections, imperfect disconnection between strut and whalers. So this was the cause of the initiation of the damage. So there are two scenarios. Scenario A is the large earth pressures than assumed in the design. Due to the overestimation of the soil strength, the deformation was calculated smaller than actually happened, and then the collapse might have taken place because of the larger earth pressures than anticipated. The other scenario, number 2, is what I explained here, based on the upheave of the materials, bringing the king post upwards, and then there is the breakage in the connection. We believe the scenario B appears to be more realistic. However, well, it is still under argument. When I look at the proceedings of the Alexandria conference, there was 2 or 3 pages description of these failures, but the major cause was attributed to this scenario. Due to the overestimate of soil strength in the marine clay, the earth pressures was underestimated. The earth pressure actually acting on this diaphragm wall was greater than that assumed in the design. The connection between the walls and the struts was not well fitted and strong enough to resist the increased lateral force. The two-in of the diaphragm wall specified to be 3 meters below the top of the stiff OA layer appears to be achieved, but because of the presence of weak zone near the top of the OA layer, the two of the diaphragm wall moved inward, causing upheaval of the bottom of the excavation, accompanied by the lifting of the king post and also by the sag of the diaphragm wall itself. Thus, an offset was produced in the connection between the walls and struts, resulting in malfunction of the bracing system. Okay, this is the end of the first story. The second talk is piping-induced failure in deep excavation in subway construction in Kaohsiung. Location is illustrated in this diagram. This is Taiwan. Taipei is here. Kaohsiung is located here. A large map is shown in this slide. There is the 2 lines, red lines and blue lines, just completed in the city of Kaohsiung. Accident took place when this orange line was under construction at this location. If we enlarge that one, it looks like this. The cavings with a width of about 80 meters and length and width of 20 meters developed on the southern side, and also there are small caving on the northern side. There was a boring BO29, BO30. This is a southern big hole. Very fortunately, this accident took place in the park, so nobody was killed because of the cave-in. Plan view of the subway line under construction is shown here. There is a connecting collider in here, and also the side view shows that the connecting collider is just here, overlaid by the thick stratum of alluvial or diluvial layer, and also there was a roadway underground just above this connecting collider. The soil profile, as shown here, indicate the SPT values on the order of 10, 20s, and so on, down to the level of the shear tunnel basis. However, consisting of SM material, silty sand, sandy silt, and so on. And when the water collecting shaft or sump was under construction, there was a piping which occurred at this location. After minutes of piping, two engineers are there, workmen were at the bottom of the pit. They tried to put the sandbags and so on, but it was not possible. The black-colored water came in, and eventually they gave up, and they went up, and they looked down. They testified that the sandbag was floating like this, something like clothes in the washes. So this is another view, looking down, showing the sandbag and so on. This is the rudder. Well, when the caving propagate reach at the level of the ground, they destroy the water supplying main, allowing a lot of water coming in. It was not possible to stop this water inflow almost 12 hours after the accident. It was not good. At the location of the accident, jet grouting was performed as shown here. This is a shear tunnel, upline and downline, and this is a corridor, and the water sample was excavated just down here. And as you can see, there was an overlapping of the jet grouting unit, specified to be 60 centimeters as shown here. But because of some reason, this overlapping might have been smaller than 60 centimeters, which might be the responsible for triggering the seepage failure. This is a detail of the failure at the time. This is a tunnel connecting collider. Opening was excavated in dry condition by putting the support, ring support here downwards. But just at this location, when the construction was completed, 90%, there is the collapse of a small chunk of soil about this size, just came in. And then followed by the waters piping in to this space, and gradually it increases, bearing all the spaces. So engineers went off and put very stiff lead at the opening, and then there was a support. However, the leaching started from here, propagated in the outer zone, and then the tunnel shield segment started to deform, and water started to cascading from the ceiling into the already completed shield section. And then it propagated finally to the ground surface. So this is a series of pictures I have drawn for illustration. At the beginning, this is the starting point of the seepage failure due to internal erosion of the material. As you can see, this is 24 centimeters. This is 24 centimeters. However, it is highly likely that the water, mud water, came from the bottom towards this already completed water sunk. Because when we solidify the materials by jet grouting, it is not conceivable that the water will migrate horizontally. Most likely it will come from the bottom upwards, vertically. This is a stabilized zone. This is a shear tunnel, corridors and sunk. And this is the roadway on top of this sheared machine. As you can see here, there is a 6 centimeter in diameter water supply main pipe, which was also collapsed, supplying a lot of water into the already completed shear tunnel. This is the second stage of the failures progressing from here to here. And then as a result, this solidified portion appears to tilted as a fall, bringing the material into the this water sump and breaking this lid, and the mud water spread here and there. At the same time, offset developed in the sealed connection, allowing a lot of water cascading from the ceiling into here. And eventually, this propagated very appreciably, allowing every soil mass fall down into this sealed tunnel. And at the same time, because of the tilt of this connection, there was an opening at the joint, and then there was another water-saturated material coming in from the northern side. So eventually, it became like this, involving the collapse of the water main near the surface, supplying a lot of waters into the sealed tunnel. So if we imagine this series of things in the longitudinal direction, it looks like this. First of all, the piping took place at this location. This is an enlarged map. This is a sealed tunnel already completed. This piping supplied mud waters into this hole. As a matter of fact, every engineer testifies that the materials in that region is very black, containing black non-plastic silt. That once this silt smear the shirts, the black smear cannot be washed away. So this is a particular material, I guess. So this is the third step of illustration involving the flow down of the materials into through the breakaged, broken pieces of sealed segments into the already constructed tunnel. So eventual situation of the collapse looks like this. I should say this cost almost, say, $10 to $20 million for repairs. The previous Singapore collapse claimed much more money, amounting to more than $100 million. So I would like to attribute this accident to the shortage of the soil investigation. So if the soil investigation had been done more in detail and the study had been done on the soil properties, this kind of accident might have been avoided. So as a result of accident in Taiwan, I investigated a lot of papers regarding the seepage failures. As you might know, there is a segregation seepage which is associated with the seepage failure from the core of the dam into the downstream more coarse material. This criterion has been established initially by Tirusagi and modified to some extent by other engineers such as Skempton and so on. But anyhow, these phenomena is associated with soil having gradings as shown this red line. And on the other hand, Dr. Sherrard, I think you might know his name. I pay a lot of respect to him after reading his paper. That is a very nice paper. Sherrard made studies on the erosion by explosive clay. And if the clay is explosive, the erosion-induced tunneling and gully formation can be easily formed. So Mr. Sherrard proposed a criterion to identify whether this erosion can take place or not. But this is associated with this green grain size distribution. What we observed in Taiwan doesn't belong either of these gradings. It belongs to these areas. So we thought this is a new area to be studied or to be explored, its mechanism. So at this moment, Professor Wei Li is now constructing a new simple shear, direct shear apparatus where some flowing seepage is allowed from the top to the bottom, and then shear deformation is applied afterwards or beforewards. So simple test has been done at that time, as shown in this diagram. This is a soil sample, only 4 centimeters in height and 5.17 centimeter in diameter, covered by the gravel upwards and also gravel downwards. There is the filter mesh, and then water pressures on the order of 98 kilopascal is applied, and water is allowed to flow from here to here. This is only a 3 millimeter small hole digged at the beginning. So this is called generally the pinhole test. The specification is given to ASTM standard. So after allowing water to seep, then it was possible to watch the water colors. For comparison, we took another sample from the Japanese site of tunnel construction where grain size distribution looks almost the same. The white one is from Kaohsiung one, and this triangular mark indicates the grain size distribution from Japanese site. This is just the grain size distribution curve comparison, Kaohsiung sand and Japanese sand. Well, this indicates the sample top, sample bottom, and surface of the sample. After percolating the water in the middle, through the small pinhole in the middle, the water was collected, indicating the very dark, turbid colors as shown here in the first 1 minute percolation. In the second 1 minute percolation and third and fourth minutes of percolation, water becomes almost transparent. This kind of things appears to indicate actually the Taiwan silty sand have a special silt which is very erodible internally. This is a similar result of tests performed on Japanese sand, where you can see there is no turbidity, no color change. The material from Kaohsiung sand is also tested in the same manner, but it refers to the test results on undisturbed samples. Similarly, color changed in the first 1 minute percolation. The another things we have done is the measurement of specific surface, which is defined as the surface area divided by the volume of the sand grain, which indicates, as shown here, for Kaohsiung sand, the specific gravity indicates a number of 3.11, and the silt from Japan indicates 6.1849. So apparently, the silt in Taipei looks like rounder as compared to the Japanese one. If it is rounder, the small particle existing in the structures of the large particles tends to move very easily if it is subjected to the gradient of the seepage water. This might be the mechanism. However, further on, we haven't done any tests like this. Dr. Lee will probably do this kind of test further on. So scenario of collapse, piping had occurred through the stabilized silty sand deposit under the water sump. The hydraulic gradient along the probable seepage path is assumed to be about 12. That is counted as 24 centimeter divided by almost 30 meters water depth. Number two, one of the factors leading to the piping is conceived to be high susceptibility to internal erosion of silty clay fraction of about 30% obtained in the local sand deposit of diluvial origin. Number three, a large quantity of water from the breakage of the supply pipeline aggravated the degree of damage. Okay, the third cave-in of Shanghai have not investigated so much in detail. I would just like introduce the features of the damage. I collected as much information as possible from my colleagues from China, who is now working in Japan as professors at Nagoya University. This is the Yangtze River, and this is the river. Shanghai city is located here, and the World Fair was operated here. That was the story of 2003. This is a subway line construction on the left bank of the Hangpu River. Accident took place. This is the opposite pictures. I'm sorry. The lower portion indicates the north. And the subway construction was completed here, and there was a connecting corridor. The material consists of gray clay, fine clays, and all the way down to a depth of 50 meters. The local people told that the material is the same. Now, the consequence of the failure looks like this, involving tilting of stories, and the most dramatic was the tilting of the almost 30 stories high, supported by piles. I heard that the tilt was almost 71 7-centimeter difference between here and here, but still that building is being used. Since the accident took place near the river, there was a fear of inundation of the water into the city area. So army force was mobilized, and then the internet broadcast was cut off by the government. And this indicates how water came in to the street, how people are struggling against the incoming water. This picture shows the rough diagram I quoted from the pictures, from the figures they provided to us. According to their account, the construction of the tunnel was completed, and at the same time, corridor was constructed, and together with the ventilation shaft. The freezing technique was installed to advance construction in this complicated area. And however, because of the electricity cut or malfunction of the machine, the frozen soil started to melt. And this was the reason for such a big accident, I was told. But the real story is not known, because the engineers involved in this work was arrested, and nobody knows where they are now. So there is no means to make any hearing. So, and one of the things which is concerned with the design is that normally we don't put ventilation shaft together with the crossing collider. The ventilation shaft should be located at other place. The design to install ventilation shaft just on top of the colliding path is a not good design. In Japan, we never do this kind of things. So this is the more enlarged areas. This is the northern direction. This is the ventilation shaft. This is the two lines. Now it is okay. We visited the site 2 years ago, and I looked into the ventilation shaft from the ground surface. Everything is fine, and the subway is now in operation. So scenario collapse, malfunction of the ground freezing method is said to have triggered the collapse. A thick alluvial deposit of silt and sand in Shanghai district is conceived to have a characteristics which is vulnerable to piping and flow type failure. A general concluding remarks is written here. In the case of collapse at Nickel Highway in Singapore, presence of the buried valley at a depth 30 to 35 meters was not clearly identified in the feasibility study stage, with boring data at an interval of 20 to 30 meters. In addition, soil properties near the top part of the underlying seemingly stiff layer was not investigated in details, resulting in an awareness of less stiff soil deposits being existing there. Thus, the depth of embedment of the diaphragm wall into the sufficient stiff layer was short. The situation appeared to have led to lateral displacement of the toe of the diaphragm wall, leading to the upheaval of the bottom of the excavation. Thus, upheaval must have caused the uplifting of the kink post and led to the offset at the joint between the strut and walls. Incident in Kaohsiung. In the case of caving of the ground at Kaohsiung, the piping occurred when open excavation was underway at a depth of 34 meters. The nature of the local silty sand was shown to be possessed of peculiar characteristics in that the silt-sized particle could be detached easily from the skeleton composed of larger particles. This particular nature of local silt, having high susceptibility to internal erosion, must have critical hydraulic gradient, which are much smaller than that of normally encountered silt in other areas of the world. Incident in Shanghai, although detailed information is lacking, it appears likely that the peculiar nature of thick deposit of silt in Shanghai alluvial plain, such as high susceptibility to erosion or piping, must have been responsible, partly or wholly, to induce the large-scale collapse in the deep excavation of subway construction. So, as a whole, we can say that close examination of topography of buried valleys and the thick alluvium and the property characterization in the base layer should be made. Characteristics of local soils or clays to seepage instability is an important factor to examine in details. Soil investigation are shown to be by far more important than anything else for reducing the risk of construction and for implementing cost-effective construction works. This is my end of my presentation. Thank you.
Do you have any questions? Marcelo.
In the case of recent Shanghai, I understand that the overestimation of the shell soil was not only because the thermal condition was wrong, but because the software, the final code used for the design of the diaphragm wall was bad used. So the people working on the design didn't follow the procedure that the software recommends you to do, and that they don't overestimate the price of decline. Are you familiar with this?
Well, the only soil information available there is SPT, which they said on the order of 5 to 10 all the way down to a depth of 20 or 30 meters. No detailed information was available for me. And also, they said there was a diaphragm wall constructed. And also, inside the diaphragm wall, if we look at it very carefully, there is a trace of jet grouting, but it was not verified very clearly. I think there was a jet grouting installed inside the diaphragm wall. So the common features for 3 accidents say that it occurred about 30 to 34 meters. This is one thing. The secondly, 3 of them employ jet grouting. So jet grouting practice is very important. If it should be very carefully implemented. If the principle is applied directly to the practice without any previous experience, we cannot put 100% reliance on the jet grouting.
In the collapse in Taiwan, where you had that jet soil gravity stabilized element, if that had been completely jet stabilized, cemented, that piping couldn't have occurred, could it?
Well, I heard it was jet grouted. The material surrounding the collider was solidified by means of jet grouting from the top through the highway space underneath. Yes. So because of some obstacles on the ground related with the ventilation of the roadway underneath, so the jet grouting could not be performed in plumb, vertically. Yeah. So there might be some small overlapping.
That could be the primary cause of the failure, right?
Yeah, but it is not. It could not identify. After the collapse, again the diaphragm wall was constructed surrounding the all constructed area. Then excavation was performed. Everything was taken out, and we had a lot of pictures showing how buried structures was located. But I'm sorry, I cannot. I don't. I have not prepared for the slide. Yeah.
I have a question on the. We'll get to the bottom of that. On the Singapore failure, was there any measurements of the center post and of the diaphragm wall in the vertical direction?
I made some question about this, but there was no. So in Japan, there have been several cases of measurement of uplifts of king post. They say that about 10 centimeters, 5 centimeters or 10 centimeters was the maximum observed uplift.
I think this, some of the measurements that I showed you this morning at the national site, we've measured that whenever you have a top-down wall, you start excavating, there's a lot of down drag that takes place between the mass and the wall. And I wonder if there was a significant amount of down drag from the paint mass on the wall.
I think there was not significant amount, but they didn't measure. So they did not mention loudly about the sag of the diaphragm wall.
Well,
Look like with these soft marine soils, they could have used bone penetration testing.
Yeah, of course, there has been a lot of extensive soil investigation regarding soil property itself. Yeah. So there is a underend consolidated underend strengths values and also the compressibilities and characteristic of the formation. All these things were studied in the laboratory.
after the fact or?
No, even before that. Yeah. Yes.
Ms. Martin?
Back to the Singapore case. you presented at the end 2 case scenarios for the mode of failure. I don't know if we can go back to the slide, but from what I saw in the pictures, and is it possible to learn that we should brace in the vertical direction the many levels of struts? Structurally, will that help? Yes.
You mean the...
Well, now that we have this slide, I want to see if it's possible to have a vote. Who would vote for A and who would vote for B? Because I voted for one from the first few slides for one of the two, but I like to see the opinions. Maybe there's case B, case C too. So these are 2 questions: a vote, and second, if bracing in the vertical direction would have helped.
You mean the
different?
bracing in the vertical direction? What do you mean?
Yes, in
This one?
correct. As you excavate, you brace with
This one?
correct. So that the differential movement between the enclosed and the side perimeter walls would be stiffened.
Yeah, of course.
Because what happened is this differential movement caused a P delta effect on the struts, which failed, and then one side collapsed, the other followed.
Yeah, that's correct. Yeah, that is.
If this box inside was very solid, or solidified with few extra bugs, I think the failure would have been more local. That's my opinion.
Okay. Yeah, that is a kind of design issues. Normally speaking, this spacing is about 2 to 3 meters. And king post is distance is about 10 meters and so on. So the arrangement of the temporary supporting structures has been designed based on the conventional procedures. So there had not been any dispute about the number of support and also the king post arrangement. However, there is another opinions. As you can see, there was a curvatures. There is a curvatures in like this. So this kind of things might help to induce collapse. But we don't believe this contributed so much.
Thank you very much.
Okay, thank you very much.
This is the plaque, and it says Texas A&M University, Zachary Department of Civil Engineering, in recognition of Professor Ishihara's presentation of the 18th Buchanan Lecture. The title of it is Forensic Diagnosis for Site-Specific Ground Conditions in Deep Excavations of Subway Construction.
Thank you.
Thank you very much.